I'm Stephen Edwards, and I'm going to talk about advanced 6502 assembly language programming for the Apple II series of computers. I've been coding in 6502 assembly language since about 1982, so about 80% of my life. Here I am in a magazine article from around then, bragging about how I was going to be programming the Apple II in assembly. I clearly remember the day I figured it out. We were cowering in our basement during yet another tornado warning, and I was reading the Apple II reference manual, Steve Wozniak's gift to hobbyists and cloners alike. This book is a marvel, and it actually came with a computer. Yes, I'm old enough to remember when computers came with useful documentation, but mind you, this was the last millennium. This book tells you absolutely everything about the guts of an Apple II, including character set information, lists of I/O locations, diagrams on the perverse memory layout of the text and graphics displays in the Apple II, schematics, monitor ROM listings, and, most relevant to my story, an appendix on the 6502 instruction set, about the driest introduction to 6502 assembly language you can imagine. I remember when I cracked the code that night, when I first understood that everything had to go through the accumulator on its way to and from memory. But I'm getting ahead of myself. It's good to understand the context of the processor if you're going to program it. At the start of 1975, there were a handful of viable single-chip 8-bit processors. The Intel 8008, which had been around since 1972, only cost $25, but ran at 500 kHz, only had a single external 8-bit bus demanding specialized or numerous support chips, had a meager 3,500 transistors, and could only address 16K of memory. The Intel 8080 came along in 1974 and was a substantial improvement. It could access 64K of memory with its separate 16-bit address bus, consisted of 6,000 transistors, and ran at 2 MHz, but sold for a premium, $150 at the end of 1975. Nevertheless, the 8080 ended up in the heart of the Altair 8800, which launched the first personal computer revolution, and its successors, the 8086 and 8088, gave us the behemoth known as the IBM PC, which we've been stuck with ever since. Motorola's 6800 had also come out in 1974 and was comparable to the 8080, but simpler. It had only 4100 transistors, ran at 1 MHz instead of 2, and had a smaller register set. Motorola was selling it for $175. A group of folks who worked on the 6800, including Chuck Peddle and Bill Mensch, left Motorola in August of 1974 to build a simpler, cheaper processor to compete with the 6800. Thus was born the MOS Technologies 6502. It reached the market in late 1975 at a price of around $25, thanks in part to its low transistor count of only 3,510, about that of the 8008. But it was far easier to use than that Intel chip. As you might imagine, there was quite a lot of drama and litigation surrounding the genesis of the 6502, but that's a different story. To understand the 6502, let's work from the outside in. Its pinout is straightforward, but worth understanding. Packaged as a 40-pin DIP, most of its pins are devoted to its 16-bit address bus and 8-bit data bus, which allows it to access 64K. The remaining pins include a single 1 MHz clock, a read-write signal, interrupt and reset inputs, sync and ready pins that can be used to single-step the processor, and a single 5-volt power supply. The programmer's model of the 6502, which is a list of registers and other programmable visible state, is extremely simple, even by the standards of 70s-era single-chip processors. It is an accumulator-based architecture centered around a single 8-bit accumulator A, on which virtually all operations are performed. 2 8-bit index registers are mostly intended to hold address offsets, although they can be used for loop indices and other temporary storage. Rounding out the registers is the lone 16-bit register, the program counter, an 8-bit stack pointer that limits the stack to a minuscule 256 bytes, insufficient for high-level languages like C, and an 8-bit status register with the usual 0, carry, and negative bits used to control conditional branches. Thanks in part to the amazing Visual 6502 project, which I strongly suggest you Google, the layout of the 6502 die is now well understood and can actually shed light on the design of the instruction set. When we look inside, we see 3 regions. The top region is a regular-looking ROM that decodes instructions and feeds signals to the control logic, the second band of the chip, which in turn sends control signals to the data path that covers a little more than the lower third of the chip. The structure of the programmer's model is visible in the data path. It's arranged as 8 1-bit rows. The columns are, from left to right, the Y, X, and stack registers, the arithmetic logic unit, or ALU, the accumulator, and finally the program counter, which is larger both because it is 16 bits and because it includes logic for incrementing. This is a nifty visualization of all the 6502's opcodes, which I adapted from Gary Little's Inside the Apple IIe. At the center, fittingly, is the accumulator, and virtually all the interesting arithmetic instructions, including add, compare, exclusive OR, and others, operate on the accumulator in memory. The two index registers can be loaded, stored, incremented, decremented, and transferred to and from the accumulator. A number of instructions modify the stack pointer, including push, pop, and jump to and return from subroutine. Conditional branch and unconditional jump instructions modify the program counter. Finally, an additional group of instructions transfer and modify the status register. Now, let's dive into the details of the 6502 instruction set. If we're going to program it, we need to know what tools we have at our disposal. Instructions start with an 8-bit opcode and may be followed by 1 or 2 bytes of literal data, depending on the instruction's addressing mode. The encoding of the 6502 instruction set perplexed me for years, in part because of opcode matrix drawings, like this one from a Rockwell datasheet, which didn't provide too much insight. Here's a better way to look at it. The least 2 significant bits in each instruction divides the instructions into 4 groups. The top 3 bits determine the operation, such as add or subtract, and the middle 3 bits determine the addressing mode, mostly. There are many exceptions. Group 1 instructions include the familiar add, subtract, compare, and logical operations with a fairly orthogonal set of addressing modes. Group 2 instructions include shift and rotate, as well as instructions that load and store the X register. These provide fewer addressing modes than those in Group 1. The opcodes ending in 00 are more of a mess. There are at least 5 subgroups, including more index register instructions, flag control instructions, conditional branches, and stack instructions. Finally, the original 6502 didn't have any valid instructions that ended in 11. Let's go through the Group 1 instructions in some detail, since they are nearly orthogonal and present us with most of the important addressing modes. LDA loads the accumulator with an 8-bit value. This example uses immediate addressing, denoted by the pound sign, where the value to be loaded comes immediately after the opcode. STA stores the accumulator in memory. This example uses zero-page addressing, in which the address comes from the single byte following the opcode, implying that this addressing mode can only refer to the first 256 bytes of memory. It took me years to realize it, but the 6502's zero-page is meant to be treated like a large register file. Accessing zero-page memory is often 25% faster than accessing the rest of memory, not because the physical memory is any faster, but simply because the processor does not have to load a third instruction byte. Looking back, I didn't realize this when I started programming because the Apple Monitor consumes about 25% of zero-page locations. DOS 3.3 or ProDOS consumes some more, and AppleSoft consumes all the rest. Well, almost. The result is that if you're interested in doing assembly from AppleSoft, which I, at a tender age, was unfortunately attempting to do, zero-page locations are in very short supply. ADC adds a number taken from memory plus the carry flag to the accumulator. Including the carry flag enables multi-byte arithmetic, but there's no add without carry on the 6502. You just clear the carry flag beforehand. This is using zero-paged index addressing, where the address of the byte to be added comes from adding the single byte after the instruction to the X register. SBC is subtract with carry, meaning the complement of the carry flag indicates a borrow, again for multi-byte arithmetic. Byte in memory is subtracted from the accumulator. This is using absolute addressing, where the address for the byte to be subtracted comes from the 2 bytes following the instruction in little endian order. CMP is compare. Like SBC, it subtracts a byte in memory from the accumulator, but it discards the result and only updates the flags in the status register, typically for a conditional branch. This is using absolute indexed by X addressing, which takes the address from the 2 bytes following the instruction and adds the contents of the X index register to compute the address of the byte to subtract. AND is the bitwise logical operator. It reads a byte from memory, here using the absolute indexed by Y addressing mode, computes the bitwise AND of it with the accumulator, and stores the result in the accumulator. ORA is bitwise logical OR, which operates much like AND. This example is using the indirect indexed addressing mode, which is the commonly used complex addressing mode. The 6502 doesn't have a 16-bit index register. None of the addressing modes I've shown so far can let you access an arbitrary address in memory. Indirect indexed addressing fixes this shortcoming by letting you specify a location in zero-page that is treated as a 16-bit address, very much in keeping with the zero-page as a register file view I mentioned earlier. After loading the 2 bytes in zero-page, addressed by the byte following the instruction, the 6502 adds the contents of the Y register to compute the final address of the operand, such as the byte being ORed into the accumulator. EOR is exclusive OR, another bitwise logical operator like AND and ORA. This example is using the uncommonly used indexed indirect addressing mode. Like indirect indexed, the address of the operand is given by a pair of bytes in zero page, but here the address of those bytes is the sum of the byte after the instruction plus the X register. That is, the X register is added to compute the zero page location holding the address, that is, before the 16-bit address is computed. It's something like having the X register index an array of addresses held in zero page. Group 2 instructions don't support the indirect addressing modes, but are otherwise very similar to Group 1 instructions and are largely orthogonal. LDX loads a value into the X register, such as a literal. Of the Group 2 instructions, LDX is the only one that can use a literal like this. STX stores the value in the X register into memory, here at a zero-page address. Inc is a read-modify-write instruction that adds 1 to the value of a byte in memory, here using zero-page indexed addressing. Dec does the opposite of inc, decreasing the value in memory by 1. ASL is arithmetic shift left. It shifts bits left by 1, shifting a 0 into the least significant bit and shifting the MSB into the carry flag. This example is using the accumulator addressing mode, where the source and destination is the accumulator by itself. ASL and other bit shifting instructions can also perform a read-modify-write operation on memory. LSR is logical shift right. It shifts the bits right by 1. The most significant bit becomes 0, and the least significant bit goes into the carry flag. This example illustrates a bit shift instruction used with a read-modify-write addressing mode. ROL is like ASL, but it takes the new LSB from the carry flag, enabling multi-byte shifting. ROR is like LSR, but it takes the new MSB from the carry flag. Now we're into miscellaneous instructions that generally follow few patterns. For example, LDY, STY, CPY, and CPX are analogous to their accumulator-centric variants, but can be used with only a few addressing modes. JMP is an unconditional jump, which comes in 2 flavors. This is the more common version, where the 16-bit target address is held in the 2 bytes following the instruction. The other addressing mode of jump is unique. Again, the 2 bytes after the instruction specify a 16-bit address, but unlike before, they are treated as the address of the target address to be read from memory. That is, this is a little like indirect indexed addressing, where a 16-bit address is read from memory, but rather than insisting the address reside in zero page, the address can reside anywhere in memory. This addressing mode is rarely used, but finds use in the Apple II monitor's CSW field, 2 bytes that contain the address of the routine currently responsible for printing a character, typically to the screen, but this can be changed to, say, send the output to a printer. The bit instruction has my vote for strangest instruction in the 6502. It loads a byte from memory, loads its 2 most significant bits into the negative and overflow flags, then performs a logical AND with the accumulator, and sets the 0 flag based on the outcome of the AND, without changing the accumulator. It's probably most useful for checking the MSB of an I/O location, like the keyboard strobe, but the AND with accumulator functionality can also be used to check if 1 or more other bits in the byte are all clear. Here's a collection of single-byte instructions. These increment and decrement the index registers, which is useful when doing counted loops, shuttle the contents of index registers to and from the accumulator, and provide the rarely used ability to save and update the stack pointer. Here are more single-byte instructions that can set and clear various status register flags. The carry variants are used often in conjunction with ADC and SBC instructions. The 6502's decimal flag is quite unusual for a processor. When set, it makes the ADC and SBC instructions calculate with binary-coded decimal instead of binary. This is one of the few aspects of the 6502 that was ever patented. However, I know of little use of this feature. The 6502 variant used in the Nintendo Entertainment System went so far as to remove the decimal mode circuitry, since it consumes a fair amount of area in the ALU. The 6502's conditional branch instructions are straightforward. Each is followed by a single byte containing a 2's complement program counter relative offset, limiting conditional branches to a range of roughly 127 bytes. Each branch tests one of 4 flags in the status register, namely negative, overflow, carry, or 0, and each can be checked for being set or clear. The 6502's stack-related instructions round out our discussion. The stack is used primarily for storing subroutine return addresses. The JSR, jump to subroutine instruction, pushes the 16-bit program counter on the stack and sends control to the address in the 2 bytes following the instruction. The RTS, return from subroutine instruction, undoes the effect of a JSR, popping the return address from the stack. The rarely used RTI, return from interrupt instruction, works like RTS, but also pops a saved status register value from the stack, where the 6502's interrupt handling mechanism pushed it. The processor status can also be saved and restored from the stack with the complementary PHP and PLP instructions. The PHA and PLA instructions push and pop the accumulator value on the stack. These are commonly used for temporarily saving a value, since you don't have to worry about managing the memory for the value. BRK is break, which is a software interrupt that can be used for stopping programs when you are debugging them. Its instruction code is 0, so sending control to uninitialized memory often leads to a break instruction being executed. Finally, NOP is no operation, a surprisingly useful instruction that can be used to increase the delay of a timing loop or patch a buggy program without reassembling. Now let's talk about programming this beast. To illustrate a number of coding techniques, I wrote this little demo program, which performs this eye-catching but physically inaccurate simulation of 30 bouncing balls. I started with a vision of what I wanted this bouncing ball example to look like, which I knew would consist of some initialization followed by the simulation of the physics of the balls. Here's the pseudocode. My code begins by clearing the first high-res screen and then switching to it. Doing it in this order hides the surprisingly slow screen clearing process. Next, I draw the frame, 2 horizontal lines and 2 vertical lines. This is fast enough so you don't see it. Next, I set up the positions and velocities of all the balls, and then draw the balls on the screen in their initial locations. Then I enter the main loop, which loops over each ball. I begin by erasing the ball since we're going to update its position. Then I update its horizontal position based on its velocity and check whether it needs to bounce off a wall. I apply gravity, which just increases the ball's vertical velocity, and then update the vertical position, which may involve bouncing off the bottom. Finally, I redraw the ball in its new position. Once all the balls have been updated, I check to see whether a key has been pressed. If it hasn't, I repeat the main loop. Finally, if the user has pressed the R key, I restart the program, which I found useful for debugging. I'm going to bring you through the code I wrote to perform these tasks, but to make any sense, I need to teach you about graphics on the Apple II. To understand graphics on the Apple II, you need to understand its text mode and how WAS implemented it. The text mode on the Apple II series displays 24 lines of 40 characters each. Each character is represented with a single byte and displayed as a matrix of 7 by 8 pixels. The first Apple IIs could only display uppercase. The IIe and later models included lowercase. My 11-year-old daughter was taught to look for friendly numbers when doing arithmetic. For normal humans, things like 10 and 100 are considered friendly, but computer people know better. We love powers of 2, which is why we don't think 40 by 24 is very friendly at all. I can only imagine how disagreeable Woz must have found these numbers, because to get around them, he came up with an ingenious solution that has cursed Apple II programmers ever since. His reasoning must have gone like this. 24 isn't a power of 2, but it's 8 times 3, and I like 8. And 40 isn't a power of 2, but 3 times 40 is 120, which is almost 128. And 8 times 128 is 1024, which is 1K, which I really like. So Woz split the screen into 3 bands of 8 lines each, and put the first line of each band into the first 128 bytes, the second line into the second, and so forth, wasting only 64 bytes out of 1024 total. Now, if you look at one of those inscrutable maps of addresses of the text screen, it begins to make sense. The lines on the top third of the screen start at 400, and then every 128 bytes after that. Then the lines in the second third start 40 bytes after each of the first batch of lines, followed by the lines in the remaining third. The Apple II's low resolution or low res mode treats each character as a pair of pixels, each having one of 16 colors, giving a 40 by 48 display, or 40 by 40 with 4 lines of text at the bottom. Woz actually worked on a version of Breakout for Atari, so it's not surprising that a little Brickout was supplied with early versions of the Apple II. But I doubt the Apple II would have been quite as successful were it not for the high resolution or high res mode that Woz basically hacked into the Apple II. High res mode is a 140 by 192 pixel mode that provides 6 colors, green, purple, blue, and orange, in addition to black and white. Each high-res page, and the Apple II supports 2, consumes a whopping 8K of memory each, which is an exorbitant amount of memory for hobbyists in the late 1970s. Nevertheless, most games use high-res mode, and it's what I used for my bouncing ball demo, although I only used black and white. One of the challenges with high-res mode is its memory layout, which is like 8 text pages one after the other. Instead of representing a 7-byte pixel character, each byte in high-res represents 3.5 colored pixels in a row. And like in text and low-res mode, each row consists of 40 sequential bytes of memory. But then it gets weird. The top row starts at the beginning of high-res memory, and the next 7 rows each start 1024 bytes after the last. The next 8 rows start 128 bytes after the previous 8 rows, just like in the text mode display, and the next 8 start 128 bytes after those. Like text mode, this goes on for the top third of the screen. Then Woz uses the same trick he used for text. Starting at row 64, the addresses start again, this time 40 bytes from the start of high-res memory. This odd memory layout gives rise to the characteristic Venetian blinds effect you see when a high-res image is loaded into memory sequentially, such as from disk. The addresses make a little more sense if you look at them in binary. The lower 5 bits of the address indicate the column, mostly. The lower 3 bits of the row number appear in bits 10 through 12, and the next 3 appear earlier in bits 7 through 9, which gives the address for the first 64 rows. As in text mode, the next third of the screen, or 64 rows, are just 40 bytes beyond the first third, and the remaining 64 rows are another 40 bytes beyond that. The punchline is that Woz was able to use a single 4-bit adder to compute these addresses, which saved hardware, but left programmers with a headache. Here's the code from the AppleSoft BASIC ROMs that compute the base address of a high-res pixel. About the top 2/3 is responsible for the row computation, in part because the 6502 can only shift 1 bit at a time. This code is long and slow, which is exactly what we don't want in assembly. The solution used by most high-performance Apple II games was to throw lookup tables at the problem. These are two 192-byte long lookup tables. The first table contains the most significant bytes of the address of each row of the high-res screen. The second table contains the least significant bytes. The tables are about 300 bytes longer than the code, but are tens of times faster. This is the typical trade-off. The fastest code invariably consumes more memory than the shortest code. The best choice depends on the application. You can find these sorts of tricks described in books like Mark Pelzarski's Graphically Speaking and Jeffrey Stanton's Apple Graphics and Arcade Game Design. The encoding of high-res color pixels is as idiosyncratic as their addresses, and the story I'm going to tell is far simpler than what's really going on, but it's enough for now. Every 2 bytes represents 7 color pixels. The least significant 7 bits of each byte represent the pixels from left to right, which is backwards from how we write numbers. The most significant bit of each byte selects its palette, choosing between green-purple and blue-orange. Black and white is easier to understand. Each 0 is a black pixel, and each 1 is a white. In fact, on a black and white monitor, this horizontal high-res resolution is doubled to 280 by 192. All 0s is black. Setting the 2 least significant bits makes the leftmost pixel appear white. Adding 2 more 1s lights up the next pixel, and adding 3 more 1s and a 1 in the LSB of the second byte lights up the next 2 pixels. Bytes with 7 1s produce all white pixels. To get color, we set every other bit. For example, setting the odd number pixels in the first byte and the even-numbered ones, except for the MSB, gives purple. Similarly, setting the even-numbered bits gives green. 2 or more consecutive 1s produce white pixels, and you can mix purple and green nearby. Setting the MSB switches to the blue-orange palette. Here, the odd-numbered pixels gives blue, even numbers gives orange. Consecutive 1s give white, and consecutive 0s give black. Now 7 is another very unfriendly number indeed, especially coupled with the 6502's limited ability to do bit shifting. And so, while it's possible to draw signal pixels nearby to create a shape, it's too slow for most games. Once more, the usual suspects threw lookup tables at the problem. The usual solution is so-called Preshifted Shapes, in which 7 versions of each sprite are pre-computed and stored in memory, ready to be quickly copied onto the screen. Here are the tables I used for the bouncing balls. Each ball is 8 pixels high and 8 pixels wide, represented as 2 groups of 8 bytes, the first for the first byte of memory, the second for the byte immediately after that. Every 8 bytes in these tables represents a version of the ball shifted 1 black and white pixel to the right on the screen, even though it looks like they're going the other way. Now I can explain to you my code for clearing and displaying the high-res screen. It's straightforward, yet representative of the sort of thinking you routinely do when coding in 6502 assembly. First, I set up the gbasal and gbasH bytes in 0 page to 2000, the start of the first high-res page. But even here I'm doing something subtle. At the end of this code, X has 20 and both A and Y have 0. This was for this 3-statement inner loop, which writes the 0 in the accumulator to 256 bytes in memory, addressed by increasing Y. Note that an offset of 0 is written first, so that the B and E exits the loop when it reaches 0 again. Next, I increase gbash to move to the next memory page and decrement X. Remember that X started holding 20, which is exactly the number of pages in the high-res screen. Since it's much easier to compare a register with 0 rather than a constant, my loops usually count down rather than up. Finally, when both loops are done, I use the bit instruction to touch the two soft switches. These are memory-mapped I/O locations that switch graphics to high-res mode, then switches on graphics. I could have used something like LDA or STA, but I wanted to illustrate one use of the bit instruction, reading a memory location without saving the result. Here's my horizontal line code, which illustrates a typical kind of function linkage in 6502, namely, using whatever registers happen to be convenient to pass arguments. Here I chose to use the accumulator to hold the byte to be written to the screen and Y to hold the row number. It's very helpful to also list the global variables your routine uses, since the code that calls it might be relying on them not changing. I begin by saving the color byte by pushing the accumulator on the stack, since I need to use the accumulator for something else. I read the address of the row from the lookup tables and store it in gbasL and gbsh. Then I load Y with the number of bytes to write, -1, so I can count backwards, and restore the color byte in the accumulator by popping it off the stack. The loop writes the color byte, then goes to the previous byte. Here I want to stop after writing byte 0, so I use BPL to branch until Y turns negative. For the vertical line routine, I save the color in a 0 page location because I need to recall it quickly within the inner loop, and I'm already using both index registers and the accumulator. Here, since I want to draw up to row 1 but not row 0, I use B and E to test the end condition, which branches unless X is 0. Now let's talk about the code for drawing a ball on the screen. First, I decided to use an old graphics trick for placing sprites on the screen. I exclusive OR them onto the screen instead of simply copying them, which lets you use the same fast code for both drawing and erasing sprites. Here's the logic for the exclusive OR of two bits A and B. If you start with A equal to 0, the result is the value of B. If you start with A equal to 1, the result is the opposite of the value of B. Here's a way to graphically show the same thing. XORing with a black pixel gives the new pixel. XORing with a white pixel flips the color of the new pixel. The result is that if we start with a black screen and XOR with a white ball, we get a white ball. If you XOR the same white ball again, it goes away. Now if we XOR it a third time, it reappears. The exclusive OR technique doesn't distinguish erasing a sprite from drawing another nearby, so when two sprites overlap, their common white pixels cancel out and appear transparent, a visual artifact. Fortunately, because XOR commutes, you can redraw and erase the balls in any order. While unfortunate, my hope was that the balls would move fast enough for you not to notice this. Did it work? I knew the speed of the ball drawing function would be critical, so I wrote it starting from these inner few lines, which load a byte from the screen, exclusive ORs it with a byte from the Preshifted Shape table, stores that on the screen, then does it again for the next byte. This code assumes I've put the address of the beginning of the row into gbasL and gbsh, so the Y index register needs to hold the bytes offset in the row. That leaves the X register to hold the index into the shape tables. I decided to try to preserve the X register value between iterations, but needed the Y register for looking up row addresses, so I stored the current row number in the HGRX 0-page address. This code only displays 2 bytes in a single row. To display a ball, we needed to execute 8 times on different rows. So I wrapped it in a loop that first reads the next row address from the address lookup tables using the row number in the Y index register, which I increment before storing back in its HGRY 0-page location. After XORing the 2 bytes, I increment X, which holds the index into the shape tables. To exit the loop, I look at the lowest 3 bits of this index. If they just became 0, we just finish drawing the 8th row of some ball, so we can return. Now let's talk about how I handle horizontal movement. Since there are 7 black and white pixels per high-res byte, smooth horizontal motion demands the byte number to update once every 7 pixels. While I could have stored the horizontal position as a number of pixels and divided it by 7 to determine byte and shift numbers, division is comparatively expensive on the 6502, and we aren't moving the balls around randomly, so I wanted a different approach. Another issue was that I wanted the balls to move at fractional speeds horizontally and not just 1 or 2 pixels each time. This meant that I needed some bits that would represent fractions of a pixel horizontally. Then I remembered, since each ball is 8 rows high and I am storing the bytes in order, the second shifted ball is at offset 8, the third is at offset 16, and so forth. I decided to represent the horizontal position of each ball with 2 bytes in tables called ball XL and ball XH. Ball XH contains the byte offset of the ball, which ranges between 0 and 39. Ball XL contains the shift number of the ball times 8. Storing it this way provides 2 advantages. First, the shift number is already multiplied by 8, ready for indexing into the shape tables. Second, the least significant 3 bits allow me to model moving as little as 1/8 of a pixel at a time, which makes the motion smoother. Here's the first half of the horizontal movement code, which assumes the ball numbers in the X register. First, I add ball dx, the horizontal velocity, to ball XL. Now, if the result was negative, this means the ball moved to the previous column, and we need to correct for this. So we add 56 to correct for the underflow, which we can do without clearing the carry since we know it was set, and decrement the byte number. If the byte number reached 0, we know we hit the wall and branched to bounce X. Otherwise, we're done. When there wasn't any underflow, we next checked for overflow. We first saved the updated ball XL value, which may be wrong, since we check for overflow by subtracting 7 times 8, or 56, and checking whether a borrow occurred. If the carry was clear, there was a borrow, meaning the shift number was in range, the byte number does not need to be adjusted, and we can branch to X done. Otherwise, we store the now corrected shift number, increment the column, check to see whether we've hit the right wall, and if so, bounce by negating the horizontal velocity. Note that this all assumes the ball isn't moving too fast horizontally, which I ensure when I generate the initial velocities. I also use a pair of bytes to represent the vertical position, but encode them more simply. The high byte in ball DYH is the row number. The low byte in ball DYL represents fractions of a pixel vertically. The vertical code starts by applying gravity, which increases the vertical velocity by 1 pixel per update, then adds this to the current vertical position. This sequence of instructions is standard for adding 2 16-bit numbers. Finally, I check to see if the vertical position has exceeded the bottom. If it has, I fall through to the bounce code. Since we may be moving quickly near the bottom of the screen, the simple reverse velocity procedure we use for horizontal movement doesn't work here. Instead, we reflect the vertical position around the bottom line by subtracting the y value from twice the value of bottom. Why twice? If y is just a little more than the bottom position, twice times bottom minus y is just a little bit less than the bottom position, as desired. Finally, we negate the vertical velocity by subtracting it from 0. Both these instruction sequences illustrate the standard way to subtract 2 16-bit numbers. This is hardly the final word on 6502 or Apple II assembly language programming. My graphics code is still comparatively simple since it does not perform page flipping to avoid flicker, and it's only black and white. And there are many more tricks to 6502 assembly, including many variants on using pre-computed tables, self-modifying code, and even dynamic code generation, all of which have found use in various programs that push the 6502 far beyond what its designers intended. Regardless, I hope this has given you some insight into the 6502 instruction set and how to use it to write interesting code for the Apple II series. The source for my bouncing balls example can be found on my website, which is an easy Google away.